Nu äter du den.
Okay, good afternoon. So let us continue the lesson. So if you remember last time, we talked about more or less a new concept in combinatorics, and that's the concept of combinations, in which actually the combination is important, not the order. So, for example, if I can tell you, if I ask you there are 10 students, for example, there are 10 students, and then I want to choose 5 of them. Okay, in how many ways I can choose 5 students out of 10 students? So in this kind of problem, naturally, the order is not important. The combination of the students that I am going to choose is relevant. So then it means that I am facing a combination problem. Yes? So, and then we learn there is a formula for that, and we also prove why the formula is working. And the formula is this. So we have C and R. We read it as choose N and R, and or combination, but I told you that there is also more common notation that I usually use this one. I put N top on top and R below, and then I call it again choose NR, and choose R, sorry. And hopefully you remember the formula is whatever comes here factorial in the numerator, whatever comes here factorial in the denominator, and then multiplied by the difference of these two numbers factorial. Yes? And this is when n is a natural number, and then r is also a number, a natural number, and r is somewhere between 1 and n. But of course, we also learned that for the special case that r equals to 0, this formula also works. Yes? So we also learned that if I ask you to calculate this symbol for r equals to 0, then if you calculate, it becomes n factorial. This becomes 0 factorial, n minus 0 factorial. But 0 factorial by convention is 1, and that's also a good reason why 0 factorial is a good convention to be chosen to be 1. So this is n factorial, and that's also n factorial, so it becomes 1. Of course, the interpretation, I don't know, it depends to your taste. We can say that I have n students, in how many ways I can choose none of them. Yeah, we can say that that is also one way. You just ignore them, yes? Okay, and then we started solving some problems, and then I want to continue more examples and complete it. And I think at most in 2 sessions this chapter also will be finalized, okay? But before, let me see where we can start from, yes. So let me ask you some questions. Consider that you have 10 physics books and then you have 8 math books. So if I ask you in how many ways you can choose 5 physics books, 5 physics books, 5 physics, and then 4 math, and arrange them alternatingly. Yeah, so the question is that I have 10 distinct physics books, 8 distinct math books. In how many ways I can choose 5 physics books and 4 math books and arrange them alternatingly in a shelf? Yes? So when I talk about arrange, it means that at the end order matters, yes? Okay, so how can I do that? How can I solve this problem? It's a very simple standard problem, yes? You have a collection of 10 physics books here and 8 math books. you can break this problem into some stages, yes? For example, stage 1 is choosing 5 physics books out of 10 physics books. In how many ways I can choose? Choose means that I can take them and I have it in my hand, yes? I haven't arranged them yet, yes?
If I should write it in combination, then
Yes.
it would be 10 above.
10 above, choose, 10, choose, you read it 10, choose,
And then 5.
5. This means that now I know I have decided about which books from physics group I want to take. But the next stage is to do the choice for the math books. I'm supposed to choose 4 out of 8. Yes? The second stage is choose 8, 4. Now my collection is in my hand actually. Now my task is now to arrange them in a shelf alternatingly. Yes? That is also some problem we already solved. Yes? So now you have 5 items for physics and 4 items for mathematics. You want to arrange them alternatingly. So from which I should start? Yes?
You should start with the physics book.
Physics books. So in total I have 9 positions that are supposed to be occupied, but definitely I have to start with the physics book. So the odd positions will go for physics and the even positions will go for mathematics. So I have 5 physics books. I want to arrange them in the location 1, 3, 5, 7 and 9. Yes? In how many ways I can do that? 5 distinct objects, 5 distinct locations. This is the most standard problem in combinatorics, and that is 5 factorial, yes? And then after this is done, the task is not finished yet because I have to make it clear for math books as well. So in how many ways I can arrange math books in the leftover positions which are even? 4 factorial. And then should I add them or multiply these numbers?
Multiply.
We have to multiply, yes. That's the answer. Is that clear? So that's a very simple and a standard problem. So you see that I want you to understand this point that even though at the end this is a permutation problem because the order matters, but still you have some combinations going on as well. Yes, that's good to know. Okay, let me ask you another question. So let me ask this question. In how many permutations, you see again, I am asking about permutations. In how many permutations of the letters A, B, C, and D, and E. Yes, A comes before B, and B comes before B, and B comes before C. By the way, here by before, I don't know what is it a good English word or not, but I don't mean immediately before. So I think the word is correct. Before means, of course, if it is immediately before, that's also acceptable, but I don't have that constraint. So for example, is this arrangement one of the possible arrangements A, B, C, D, E? The answer is yes, because here A is before B, B is before C, but A is immediately before B, and B is immediately before C. That's acceptable. But this is also acceptable. A, I have E, for example, I have D, I have B and C. This is also acceptable, because A is before B, B is before C. And this is, for example, A, E, B, D, C. That's also acceptable. Yes, because A is before B, B is before C. So I mean this, in how many permutations A comes before B and B comes before C. Again, you see, I am asking about permutations. I'm not forcing you to think about it in this way of combinations. In combinatorics, you're actually free, whatever you want to do, but the final answer should be right. Okay, I want to give you a little bit of time to solve the problem, okay? Okay, do you have any idea how to do that? When I was writing this, I know long back, might be I was thinking using combinations is easier to solve this problem, but I really don't, I think you can do it a little bit differently now. But anyway, do you have any idea how to do it?
Just not with combinations.
No worries about combinations. You can just write your strategy and I can also solve it in my way. If they match, that's good. If not, we need to see which one actually is right. But do you have the strategy to count it?
I have a very lengthy and unnecessary strategy.
Okay, so let us keep it for the time being. Is there any better efficient strategy to do that? I was thinking you can do like this. If I want to arrange all these letters, I need 5 positions, yes? 1, 2, 3, 4, 5. So in principle they are numbered because they are distinct. I do not have any constraints for B and D. So what I do, that is the reason that I really don't know why I have written this example when I was doing combination. I was thinking in this way. So there are 2 letters, B and D, C, which one? D and E. No constraints about them. So they need to occupy 2 locations. Yes, that's one way to see that. So I choose 2 locations out of 5. By choosing, it means order doesn't matter. So it means that I have 5 distinct locations, I choose 2 of them. By choosing means I cross them with the same thing, so that if I replace them, I do not feel it, yes? Now, these 2 should be occupied with these letters. Now I will take, now the locations for D and E is clear for me. I take them and I want to put them there. In how many ways I can put them there? 2 ways, yes? Either I choose this one for D, this one for E, or the other way around. So in principle, I have 2 distinct locations now that I want to fill it up with 2 distinct objects. So a standard problem. So it becomes times 2 factorial. Yes? Which of course I intentionally write it 2 factorial, but you can just write 2. And now what is happening? The first stage of the problem was to choose 2 locations for D and E. This is done. The second stage of the problem is take these 2 and put them in the chosen locations. That is also done. Now what is left for me is to put A, B, and C in the leftover locations. In how many ways I can do that if I want to respect the constraint? What? 1. So that's the problem. The problem is solved, yes? Now, instead of thinking in this way, I really want you to have an alternative in your mind, yes? What is that alternative? In the first one, I don't need to choose and then arrange, because I told you the form when I was designing this question in this part, probably I was thinking only in this way, but now you see that I have 2 distinct objects, yes, and then how many distinct locations I have? I have 5. Do you remember I told you it doesn't matter if the number of locations are larger than the number of items, or the number of items are larger than the number of locations. Both of them. If the order matters for you, you can use which formula? P. Yes? How many locations are there? 5. How many do I need? 2. Yes? And then, so it means that this takes care of both choosing the locations and arranging them. And then multiplied by 1. And of course, if you see this formula is again this. Because I told you here, do you remember what was the formula of P and R? It was n factorial divided by r factorial n minus r factorial. Oh, sorry, this one. Now you see that if I multiply r factorial by the combination, it will give you permutation. Yes? So this is why 2 factorial times this is exactly this. That is easier to solve the problem like this. Is that clear? Yes or no? But somehow, I don't know, for me, sometimes using combination and then using the factorial is sometimes easier for me to understand, and that's up to you. But now, I can use this one as well. So that was a very, very simple problem. This is the nature of combinatorics. Okay, let me ask you another question. Consider the word Mississippi again. Yes? So this word, we want to arrange them. I want to arrange all the letters in a row. So permutation, arrangement, the order matters. But I want to arrange it in a way to make sure that no two S's are adjacent. Yes? So, for example, this is not an acceptable one because these two S's are exactly adjacent. I want to, for example, this one is acceptable. M, I, S, I, S, P, I, P, S. And then one more P do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9. So I should have one more letter, yes? Which one is it?
I.
One more I, and then S. Yes. So that is acceptable. Yes? Because no two S's are adjacent. Now my question is that you start arranging all these letters. In some of them, two S's are adjacent. In some of them, no two S's are adjacent. We want to count the second. How many of this type are there? Yeah, I can give you a little bit of time again. Okay, so let us go back and then I will give you a little bit more time if you want to think about the rest of the problem. So here, how many permutations are there so that no two S's are adjacent? Do you have a strategy? We had similar problems before. We wanted to avoid the people who are fighting not being next to each other. That's the same thing, yes?
Yeah.
Okay. But so what can I do here now? So how many letters are involved?
What?
How many letters are there? 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yes. So, okay. Do you have any idea how to do that? Yes, Kevin?
You place out all the letters there that aren't S.
Yes.
And then in the spots between them,
And
you place.
and might be
Outside.
Yeah, exactly.
You place.
Okay, so let us follow your strategy. For the time being, you are ignoring S's. Then 1, 2. So what is left for me? M, I, again I, and and 2 P's. Yes. 1, 2, 3, 4, 5, 6, 7, and 4. Yes, 11. So first you say that I arrange these letters, yes? But in this one you also need to be observant because you cannot just write 7 factorial because we have divisions, yes? So it becomes 7 factorial divided by 1 factorial, which I don't need to write, 4 factorials, and then 2 factorial. This is the number of ways that I can arrange these letters in a row, in which order matters, yes? So for example, assume that you have done it in some way. Four I's, 2 P's. So you have done this one. But then you are supposed to arrange these S's somewhere between them or next to, I don't know, in any way that you want to prevent 2 S's to be next to each other. So what you think, you say that, okay, I have 1 position here, 2, 3, 4, 5, 6, 7, 8 positions. Okay? So this position, by the way, is distinct, yes? Because I can say this is the position on the left-hand side of the first I. This is the position between I and M. Yes? Okay, and then because all letters are S, what matters is just finding the location for these S's. Yes? So it means that I have 8 distinct objects. Objects here are locations. And then how many of them I want to choose? I use the word choose because all of them are S's, so it doesn't matter the order. So it means that I will and then I will have 8 locations. I choose 4 of them. So what do I have to do between them? Multiplication. So that is your answer. That's it. Is that understandable? Okay. Now let us go to the next problem on the board. So how many 8-element subsets of this are there such that at least 4 of their elements belong to this set? So if I just ask you how many 8-element subsets are there, this is a very standard problem because you know that in subsets we don't care about the order of the elements. So the answer would be choose 12, choose 8. That's it. But now I have another constraint here. Okay, do you have any idea what we can do here now? Anyone else? Yes?
You choose from B first, so you write 6 and then 4 below, and then you choose.
Okay, so you say that because the word at least 4, it means that either I choose 4 from here, the rest outside, yes, and inside here, or I choose 5 from here, and then 3 from here, but outside this one, and etc. Yes, and then you want to do. Let us do this. So you say that okay, first I have 6 elements in B. From these 6 elements, I choose what? 4 of them. But I am supposed to choose at the end an 8-element subset. Okay, so that the rest of it, 4, has to be chosen yet. But from how many?
So then you write 8 from, because
no, that is
I summarize it.
No, don't summarize it. Okay, I summarize it for you at the end. Okay, so what is the next one? Because based on my experience, people make mistake when they want to write the second one.
6, choose 4.
So you say 6, choose 4. So is that right, or should I write 8, choose 4?
It depends on if you split it. Kevin doesn't want to split it up into cases.
No, this question is completely clear. Yes? So you don't want to split it or not, the answers should match.
But I don't have Victoria in my calculator. Wait.
No, but I think, so others. So this means that I am choosing 4 elements from set B, and then I have to still choose 4 more elements outside B. Yes? So this has to be 6. You cannot write 8. So what Dennis is actually mentioning is correct. Yes, is that understandable? So don't think that, okay, I have chosen 4 of them, 8 of them are left. I have to choose 4 out of 8. Because if you say 4 out of 8, it means, for example, here, you might have chosen 1, 2, 3, and 4. Yes? If you write 8 from here, it means that you have given the opportunity to 5 and 6 to be chosen again. Yes? And then you are not allowed because you want to count only 4 elements coming from B. So if you want to, you should say that. Exactly 4 elements from 6 and exactly 4 elements outside. Exactly 4 elements from B, exactly 4 elements outside B. Or So this means this and it is multiplication, or exactly 5 elements from B and exactly 3 elements outside B. Outside B means 6 again. Yes? Or 6 elements exactly from B and 2 elements outside B. Yeah, this is a simple question, but based on my experience, many people get confused when they want to write the questions. Yes? Is that understandable? Yes, Kevin, now? If your answer, let me check my answer. Do you agree with me here? This means exactly 4 elements from B, exactly 4 elements outside B. Yes? Or exactly 5 elements from B, exactly 3 elements from outside B. Exactly 6 elements from B, and exactly 2 elements outside B. This means that at least 4 elements have been chosen from B. Yes? That's the answer. Is that clear? Okay. Now, this is also a good question. Consider a 7 by 10 checkerboard. How many non-square rectangles are there in this board? Because you know that squares are also a special case of rectangles, yes? But not the other way around, a rectangle, yeah, a square is a rectangle. But rectangle is not necessarily a square.
Yeah.
So you want to count the number of rectangles that are not squares. So in how many ways we can have that square in this checkerboard? So let me just draw this checkerboard here somehow.
Squares at 5, 10.
How many non-square?
Så alla de här
So 7 by 10.
7 är squares. Så då måste man ta bort. En rektangel är så länge det ena sidan
Motsatta sidan för
Ja, alltså. Det är också en kontroll. Nej, alltså jag menar bara så länge en av dem är, alltså en sida är lång och den andra är kort.
Ja, men den motsatta sidan är samma längd. Så allt blir en parallellogram.
Ja, just det.
Så därför är det enda som skiljer sig är att de inte är lika långa. De har samma krav. Jag har 2 krav. En kvadrat och 3 krav. Exakt en vinkelräta. Ska åka så här så sida ska vara lika lång. Men det är krav alla ska vara.
So this is our checkerboard. 7 rows, 10 columns. And then we want to see how many non-square rectangles I can make out here. For example, one of those is this one. Yes. This is one of the possible rectangles. This one is also another one. Yes. But if I make a square, then it is not acceptable. So I just want to count the number of rectangles that are really rectangles, not squares. How should I do that? I can pause a little bit so that you can think. The recording is continuing now. Yes.
For the previous problem,
Yes?
I'm not sure why my answer wouldn't work.
Yes, that is a hard question to answer.
I can't imagine a case where it doesn't.
Yeah, you can just tell your strategy to see how it works. The other people can still think about that problem. Yes.
Because
So what is your answer first? Tell me to write it down.
6 and then choose 4, and then multiply it by 8 and then choose 4, and that's it. But it becomes much larger.
Yeah, it's much larger because I don't understand what is the philosophy behind that. Because where is the word at least? How your solution is affected if I take the word at least from the problem?
Because the thing I'm thinking is that when you've chosen 4 from the first one, those 4 will be gone from 8.
Yes.
So then you have 8 choices left.
Yes.
And out of those 8, you have to choose 4 more.
No, but if you do that, it means, for example, in one scenario, is that you choose number 1, 2, and 3, and 4. But in your head, you are just eliminating these from A. Yes? So what are left in A now? 5, 6, yes?
And then up to 12.
7, 8, 9, up to 12. Yes? And then you say that I choose 4 from them. Let us assume that you choose 5, 6, 7, and 8. So you choose 5, 6, 7, and 8. So you counted this once. Yes? But now you count the same thing several times. Let us see why. Because assume that you choose 1, 2, 5, and 6 in your first stage. Yes?
Yeah.
Is that understandable?
Yeah.
So what are left are the things, and then you also consider them again and again and again. So definitely this number is bigger than that.
Yeah.
Is that understandable?
Thank you.
You're welcome. Okay, so any ideas about this problem? So let me ask you one question. Why are you stuck? If you want to make a rectangle, first for the time being, don't care about non-square things like that. If you just want to count all of the possible rectangles, what you can do? Can you split this task into 2 stages? Because if I want to construct a rectangle in any way, I need 2 points on the vertical axis and I need 2 points on the horizontal axis. Yes? So for example, this one corresponds to these points on the vertical and these 2 points on the horizontal. This one corresponds to this one and that one on the vertical and these 2 on the horizontal. Okay? So now if I ask you how many rectangles are there, in principle you should be able to answer that. I have to choose 2 points on the vertical axis and choose 2 points on the horizontal axis. Is this choice a permutation choice? No. Because no one recognizes if I change these 2 points. Yes? So how many points are there on the vertical axis? 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. So I choose 2 out of 8. Yes? And I choose 2 out of 11. And I multiply them. So I just want to make sure, do you understand that the total number of rectangles is this number? I am not saying they are non-squares, I am considering all of them, even squares. Is that understandable or not? Yes? But if you remember, we already know how to calculate the squares. We subtract them. Yeah, so that's a combination of 2 problems. This problem is a combination problem, but it counts all pairs here and there, including the squares. But now, if you remember our previous lesson, in principle you should remember how to count the total number of squares. Do you remember how was it? Then this is a little bit hard, so you need to combine two problems. Squares means 1 by 1 squares, 2 by 2 squares, and what is the highest dimension squares that you can have? 7 by 7 is the largest one. Yes? So how many 1 by 1 squares? So the number of squares is equal to 1 by 1 squares. How many 1 by 1 square I have? Do you remember? For squares, there is a constraint between the points that I want to choose. They have to be equidistant on the on the vertical axis and the horizontal axis. So how many choices do you remember? 1, 2. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Of course, it is very clear. So I have 10 choices here. Yes, but 1, 2, 3, 4, 5, 6, 7 choices here. Of course, it is very clear. If I ask you how many 1 by 1 squares are there, you really don't need any counting strategy. There are 70 of them. Okay, but this is 1 by 1. How many 2 by 2 I will have? 2 by 2, I need to open my fingers 2 units. Yes, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes? Then what will happen here? You can convince yourself that is 6. Yes? So this is 1 by 1. This is 2 by 2. And then I go for 3 by 3, which is how much? 8, 5. 3 by 3. Then 3 by 3. Then I go 7, 4. This is 4 by 4. Then I go what? 6, 3. This is 5 by 5. Then I go 5, 2. This is 6 by 6. And finally 4, 1. This is 7 by 7. So whatever this number is, you take this minus that one. So the question mark is equal to this number minus the number of squares. Yes, and the number of squares is this very simple sum. Yes, so that was a combination of these two problems. Okay, let us solve this one and then go to the lesson a little bit, teaching a little bit new things of today. Consider two parallel lines L1 and L2. We consider 6 points on L1 and 8 points on L2. Oh, you have also one problem here. How many triangles can one construct on these 14 points? 6 plus 8. How many triangles I can make here? So if you don't mind, let me just write it here. So consider two lines that are parallel. L1, L2, they are parallel. And then how many points I have on L1? 6. So let me call them A1, A2, A3, A4, A5, and A6. And then I have points here, let me call them B1, B2, B3, B4, B5, B6, B7 and 8. Okay, I want to make triangles using these 14 points. How many triangles are there? Yes?
First line, choose 2 points from the first line, 1 point from the second line, and then add 2 points from the second line, 1 point.
Exactly. Is that clear for everyone? So there are two types of triangles involved in this problem. The problem that a triangle like that, so don't consider this. I am considering this and that to be one triangle. Or I can choose 2 points from here and 1 point here. Yes? So I have two types of triangles here. If I count them and I add them, by the way, I can add them because there is no overlap between this type and that type. Yes? They are completely distinct sets. So I can calculate them and add them. Yes? Let us calculate. So it means that I choose, for this type, I have to choose 1 out of 6. So that is very simple. In how many ways I can do it in 6 ways, but even if you don't like it, you can write choose 6, choose 1. If you calculate this, it becomes exactly 6. So you really don't need to write this, you can just write 6. But this stage is not done, this task is not accomplished. I have to choose 2 points from the bottom line. So this becomes what? 8, choose 2. Or the other way around. I choose 2 out of 6 and 1 out of 8. That would be the answer. Yes? Let me calculate this answer, because this becomes 6. If you calculate this, it becomes 28. 8 times 7 divided by 2, yes. And then this becomes 15. And then this becomes 8. So if I multiply that 120, so 168. And then this becomes 120. This becomes 288. Do you have a different strategy? The reason that I calculated because I wanted to test the other idea. Do you have another strategy to count 288 triangles here? Here, Dennis actually used the product and the sum rule. Yes, we can also use somehow the complement rule if I am right. Can you imagine about how I can count the same thing using the complement rule? If I am right, this should be working. How can I use the complement rule? The reason that it came to my mind, you remember I gave you a problem on which I have arranged the points on a circle. Yes? Here, in that case, it is very simple. If I ask you to count the number of, assume that these 14 points are arranged on a circle. And if I ask you how many triangles are there, do you really need to separate them? No, because when I say they are on the right, they are on the circle, it means that any 3 of them really makes a triangle. Yes? So then in that case, the answer would be 14, 3. But can I say this is the answer to this problem as well? Because still I have 14 points. And I want to make a triangle. Why not?
Because you might pick 3 on the same point.
And then that is not a triangle by any meaningful word. So then I use the subtraction rule, yes? What should I subtract? Can you tell me? The ones that don't give rise to a triangle. It means that if I choose 3 of them from the first line, I am in trouble. If I have chosen the 3 of them from the second line, I am in trouble. So I have to take them out. So if I am on, I don't know, if I am correct, this should work, yes?
8 of 3 and 6 of 3.
And then if you have calculator, you can calculate these numbers to see if this is 288 again. By the way, let me teach you, this is the new lesson. I want to teach you how to calculate these things a little bit simpler, yes? So let us take this as an excuse to teach this part. Okay, so I have to change, let me change and write it blue. So do you remember, I told you this is the formula for NR. N choose R is n factorial divided by r factorial n minus r factorial, yes? I intentionally write it a little bit longer, but in practice it is easier. So what I do, I write this n factorial times n minus 1 times n minus 2, and I continue until I reach to n minus r factorial. Okay, but the previous number would be n minus r, 1 more. And then I will have r factorial, n minus r factorial, and then these 2 are gone. So this is the way that I calculate these things quickly. You might say that this is longer to remember than this one. But assume that I want to calculate this. So what I write 3 consecutive integers as a product in the numerator. Yes? And then the denominator is 3 factorial, which is 6. Yes? So this is easier to calculate. Of course, that is exactly the same thing. If you write the formula here, you have to do the calculation yourself. But I want to do it faster always. This is the way that I have learned to do things. So then I prefer to use it in this way. So I will see that three numbers, this 3, I take 3 consecutive integers from 14 to 12, and then divide by this number factorial. Let us do this one here again. I have 3 numbers, 6, 5, and 4, and divided by 3 factorial, which is 6.
20.
And then here I will write 8, 7, and 6 divided by 6. Yes, this is a little bit simpler, I'm not that much. So this is 2 times. And how much is that? 140 and 42, 182, and then you've multiplied by that 384, yes? And then you simplify that, it is minus 20, and then you simplify that's minus 56. Is that number or not?
Yes.
This is
80%?
300.
64 minus.
Yeah, I think it is, yes?
It is.
Yeah, it is. So that was also one strategy. So take this one as the new lesson. You don't have to do it in that way. But as you see, it was much faster if I want to do the calculations. Understandable or not? Yes?
That doesn't equal to 200.
Yes? Yeah, okay. You told me it is. It is not?
You get to 308.
So might be I have, so this should work, let me see. So might be I have done some mistake here. 10 times this is 140, 3 times that is 42, 140 is 182. And then I multiplied by, okay, sorry, this is 364.
Yeah, and now it becomes equal.
Yeah, that's good, thank you. Okay, so that's correct. So this is one part of the lesson. Another part, assume that I ask you to calculate this. Assume that I ask you to calculate 14 choose 11. So if you want to use this strategy, still it is boring. Why? Because according to this strategy, I have to write 11 consecutive integers in the numerator and 11 factorial in the denominator, which is of course not very efficient, I mean. So the trick is to write this to be this. I want you to feel this is a very, very important property of these coefficients. There is no difference between 14 choose 11 and 14 choose 3. We can understand this equality on 2 footing, yes? One combinatorial argument and then algebraic argument. Combinatorial is more fun. Why these 2 numbers should be the same? Yes?
In one you choose 3, and in the other you choose 3 to remove instead.
Exactly. So here, I assume that I want to take 11 students for, I don't know, for Opet Foods today. Instead of reading the name of 11 students, it's much easier to read the name of 3 students that are not supposed to come. Yes? So based on a combinatorial argument, this is trivial. Yes or no? Is that understandable? Okay, but now if you want to calculate it using this, that's also trivial. This is the formula. There is no difference between this and this. It's a very important relation. Whenever these numbers add to this, the combinations are equal. And you can prove it. You see, instead of n, instead of r, I put n minus r. This becomes n minus r. But this one becomes n minus n plus r, which is r. So this is exactly the same thing. So if I ask you to calculate 14, 11, if I want to do it using without calculator, I change it to 14.3 and use this trick to calculate 14.3. Yes? Is that right? Yes or no? Okay, so that is easy. Okay, so if you don't mind, so this is one part of today's lesson. I wanted to give you this equality, that's important. And now I want to go back to solve this problem. How many of you could solve this one? Consider 10 students, S1 up to S10. In how many ways can the students stand in a queue so that both S1 and S2 are ahead of all S3, S4, and S5? And that's exactly the meaning of the words. Ahead doesn't mean exactly immediately before, immediately after, it just means ahead, yes? So if they are waiting for taking an ice cream, this means that S1 and S2 have their ice creams before S3, S4, and S5 have their own. Yes? But which one from S1 and S2 takes the ice cream first, it is not clear. It's not demanded in the problem. What matters is S1 and S2 take the ice cream first, and then S3, S4, and S5 in any order. So in how many ways we can arrange them with this constraint? Do you have a strategy?
Kind of. I don't have a calculation, but I have a strategy.
No worries. The strategies are probably the most important things here.
You begin by placing out students 6 to 10 because they don't have any restraints.
Okay. In how many ways I can do that? So your strategy is students 6, 7 up to. So there is no up to, yes? S8, S9, S10. So you are considering these students, you arrange them. Okay, in how many ways you can arrange them? Okay, so just tell me your strategy. You have these students, you arrange them, and then?
And then I place out 3, 4, and 5. And whichever positions I choose for them, I need to place 1 and 2 somewhere ahead of them in the line after that.
Okay, but is it practically possible to count? That's also important.
I'm not sure.
So let me see, what you are saying is that you consider only, this is similar to, I don't know this strategy, I don't remember, I need to think myself, but S6 up to S10, you arrange them in a row. 1, 2, 3, 5 objects, 5 positions, 5 factorial. So they are in place now.
Yeah.
There are some places between them, okay, and then what to do with them. So how many places are left? 6.
But the thing, okay, I actually realized something. So I use the same strategy as with the letters.
Yes?
But it doesn't work really because multiple of them can fit in between. I can place 3 and 4 next to each other between 8 and 9, for example.
Yes.
And with that strategy, I only place 1 between each and every one of them.
Okay, so Kevin, you are talking in a way, if this is my strategy, this is your strategy.
So my strategy doesn't work.
Okay, so you are criticizing yourself. Okay, anyway, but so let me see. I don't know exactly myself right now. So we have 10 students. In how many ways can the students stand in the queue so that S1, S2 are both are ahead of these? Yes. No, I will start with these 5. Because I think the problem in your strategy is because you don't know what to do with them after that, yes? So why not we start with them? So how many locations we need for 10 people in a queue? 10. So I would say that I have 10 locations. I need to fill them up. So this is clear. I have 10 positions. I need to fill them up. But if you don't mind, I prefer starting with these people with constraints. And I told you that as a rule of thumb, it's not always the case, but usually it's better to start with the more constraints. So for these 5 people, how many positions I need? 5. So I choose again by marking them. Marking 5 positions, yes? So I have 10 distinct locations, but I need 5 of them for these people. So I choose 5 of them. What do I mean by choose? I mean I mark 5. Something like that. I mark them, yes? And then, this is also interesting. How can I arrange these people now in these 5 positions if I want to respect the constraint in the problem? Yes, no.
2 factorial multiplied by 3 factorial.
Definitely yes. Agree with me because if I have chosen these, there is no way I have to give these positions to S1 and S2. There is no other way. Do you agree with me? So it means that now I have 2 positions, 2 and 4, which have to be dedicated to S1 and S2. In how many ways I can do that? 2 factorial. And now what is left? 3 left positions are left, and I have 3 students here. I have to arrange them, so it is 3 factorial. Yes? And what is the final? Is it finished or not? No, because we have some leftovers. 5. How many positions are left? 5. So there is enough 5 factorial. So you see this strategy worked this time. Yes? Yeah, it's a very, very nice. It's really exciting. Combinatorics is really fun. Every time you think that you have the correct answer, when you see the faucet, your answer is wrong. And then you say that no, the book is wrong. But then if you think a little bit deeper, you understand probably you were right. Yes. Yes. So that is the strategy. Is that clear that this is the right strategy to work here? Okay. So now I think you have good experience about combination problems. And then look here. I used this combination even though the problem in general was a permutation problem. Sometimes using combination makes it easier to think about permutation problems, yes? I think it's better not to continue teaching today because might be you are tired. So you have a little bit of time to practice if you want to. But I think at most in 2 sessions, this chapter no. But of course, graph theory is omitted from the syllabus, so we don't need to bother about that. So here we will have an exam for combinatorics. Yes? And then we have to decide which date you want to have it. So if you don't mind, let me pause recording. We don't need people to know about our exam. Yes. Thank you very much.